Okay, so we begin partial differential equation with Python part 2. Well, let us see where we left in the first part. So we were discussing the problem that was heat conduction in 1D, diffusion in 1D, and the equation is as simple as that: del u del t equal to del to u del x square or x square. So first order in time and the second order in space. Well, and we discretized the equation in this explicit form. On the left side, you have uij plus 1. J is your time index, let me remind you, and I is space index. Notice that on the left side, you have j plus 1, and on the right side, all are j. That means you will decide the value at the ith point, the value of u at the ith point at the time j plus 1 advance time, given the values at the older time j, right? Okay, so and we wrote a Python script. It's a very simple script that we need for this expression to implement. We wanted to know only the values u is can be your temperature, pressure, whatever, at the at some time, at any later time, so that we wrote this program. This u equal to np dot zeros 101 means you have created 101 points arrays where every point is 0, and u50 equal to 1. That means at the middle of the rod the value is 1. That is the initial point. Okay, so this is your time loop, and inside that that is a space loop for I in range 1 to 100, and you just write this expression, this recursion relation. Okay, so that is how you evaluate this u. You do it for all i's once in the I loop, and then do it for every time. You do it for every time step, you do it for all i's. Okay, and the finally after the you come out of the loop, you try to plot plt dot plot x versus u, and you then try to see this. Okay, okay, so let us see some special cases. Okay, but before that, you have given u equal to np dot zeros 101 and u50 equal to 1. You combine these two as your initial condition and boundary conditions. You could write also with a single step, right? Because you see u50 equal to 1. That means you have given a delta function at the middle, single value. But instead of that, and the all the other values are zeros. But instead of that, you could put also this narrow Gaussian. This is a Gaussian, the last step, right? Exponential minus x minus 0.5 whole square. That means the peak value is at 0.5. That is at the middle of the rod, because the length of the rod is between 0 and 1 unit. And this exponential, this is x minus 0.5 whole square by 0.001. In a Gaussian, it should be 2 sigma square. That means sigma is very small here. So that means you have a narrow Gaussian close to delta function. So if you give this expression only, that means at the middle we have some value. If you properly normalize, it is 1. Otherwise, and the all other and the each falls off on two sides very quickly. So the all other points are nearly 0. Doesn't matter whatever initial condition you give, it's up to you. And the two end points are nearly 0. It doesn't have to be exactly 0. It's up to you what kind of temperature you fix. But anyway, you are not updating the last 2 points. So that is the thing. So you could also give this. Okay, so and you get the result after some time. That means the narrow Gaussian now spreads, and you see, say after 100 time steps, you get this temperature profile. That means along the x-axis, that means you are along the road, along the rod, and y-axis is temperature, and so you get this Gaussian. As you wait for more time, you will see this Gaussian will spread, and finally it will the heat will conducted through two sides of the rods, and finally everything will be zero. Okay, since it is an insulated rod and conduction is on two sides. Okay, this thing you can with this problem, this the same problem with the same kind of written code, you can play with this, and you can vary the initial and boundary conditions, and you can check. There can be very many different kinds of solutions numerically, and that you can do easily manipulate. You can easily manipulate that, and in some of the cases you can compare with your exact results too. Okay, so suppose you have this condition. So u equal to np dot 0 is 101. That means you have put 0 to all points, and you have in this case put u0 equal to 1. That means you at the left end of the rod where the index is 0, you have put 1. That means you are hitting from the left end. That means you know the heat will propagate through the rod to the other end. So what do you expect? You expect this one should decrease, and the other points on the rod will whose values were 0 at the initial to start with, that will gain some values. So you'll see how this heat spreads along the rod from one into other. So here it is, the profile that you expected. Okay, so this is your temperature profile after some time. Okay, okay, so let us take another kind of boundary condition, little different. You can play with this. Here you have u1 equal to 1. That means not at 0, but the next point. 1 is your index. In square bracket 1 is your index. So u1 equal to 1. So you have shifted your heating point a little from the left end. So what do you expect? Because the left end is kept always 0, and the next to it is 1. So after some time, if you do this numerical iteration, you will see this is an interesting curve that is similar to, it's a very closely looking to this Maxwell distribution formula, but it's no relation with that. But okay, you get that. Okay. Anyway, so this way you can vary you can take very many different kinds of initial and boundary conditions, and with the same script you can check various possibilities. Okay, that is the game. So you take u equal to np dot 0 is 101, and you take u0 comma u100 equal to 1 comma 1. That means you are hitting at the two ends. That means the rest of the points are 0. So what do you expect? Can you think what do you expect? Maybe you expect that the heat will propagate from two ends towards middle. So whatever it is, it should be a symmetric kind of temperature profile. So that's what you get. So temperature along the length of the rod, and you see this distribution. The two ends, that is 1, 0 and at 0 and at 1, and it becomes such a thing. And more you iterate over, you wait for more time, the magnitude will reduce, and because the one it curve will little change, but the one will be kept fixed because you have kept the two ends fixed. Okay, so the two ends will be one, but this inside profile will change little bit. So curve will be, the temperature at other points will change. Okay. uh, Here is one textbook problem you have often seen in your math methods book. Suppose T0 is the initial temperature, L is the length of the rod, and you give the similar boundary conditions on two sides 0 and the other and all other points it is T0 and so on, and you got this expression. Okay, so let me see if I can go back. I don't think I can go back in this. Anyway, so you see the formula, you can look at any book. So uniformly heated rod, you gave T0 just like the previous, one previous one problem. T0 comma L equal to 1 comma 1, x equal to this 0 to L, and this u equal to np dot 1 101, and then you multiply by T0. That means at all points you have now T0. That means it is uniformly heated rod. Temperature at all the points is T0. But anyway, we have taken T0 equal to 1. Okay. And on the two sides of the rods, you maintain at 0. U0, U100 equal to 0, 0. Okay. So, and a time loop, time in range 100. Right? So, you use this expression by slicing, or you take the previous expression with I loop, doesn't matter. So if you check this, and now the in the blue um color we have written these expression, which is the exact expression I showed in the previous slide. Okay, so small t equal to 1 by 300. How do you know? I don't know, because you know the way you discretized r, what is now 0.25 means 1 by 4, so that is equal to delta t by delta x square, but you are never sure what is your delta t. Here the time in range 100, so the time is the time step, but the actual time is time step into delta t, so that is the total time. So the I don't know, since delta t you don't know in this scheme, so I tried to check the how the numerical result matches with the exact result around which time. So I guessed something and I manipulated. So I took t equal to 1 by 300, because in your expression of, in your exact expression, there is time, there is space part. So there is a summation over m or n. So I write a function f with lambda function, lambda m, and that is 2 by 2m minus 1 whole square into t0 by pi into exponential part, that in that there is a t, and in the space sign function, in that there is space. So there's two parts, this kind of differential equations. If you solve by method of separation of variables, you have two separated solutions, space part and time part, and then you combine, and then you take for all modes, and then you take sum. So for that formula, I'm writing that formula only. So you have written a function f. It's my style. You can write in your own way. I have written this f, which is a function of m, and then in the next step, you take the sum over all the m's. All the m's means sum over m's means, and the range is from 1 to infinity actually, but here I take a few values, few terms. Range is 1 to 20 I took. Okay, so this is the left side I write exact. So this is your exact expression that you have written. Now you try to plot x versus u, means numerical result that you have obtained from the time loop. So that is plotted with O, means bullet, and then x versus exact, it is plotted with line. Let's see what we get. So here is the result. You get these, I mean, you see the orange line is your exact result, and the dotted lines, dotted points, that is your numerical result. So at a certain time t, you have the two results. Uh, you quite agree with one with another. Of course, we have not analyzed the error. We can do that later. Okay, so here is another similar kind of problem in the standard problem that you have seen many times in your math methods book. This problem is from direct from Potter and Goldberg, this mathematical methods book. It says that you have an insulated rod Tx0. There's the initial condition t equal to 0, and this has two parts. Half of the rod 0 to 1, that is something 100x, and the other half 1 to 2 you have the fixed temperature, say 100. So it's a peculiar condition, and you have the conductivity given, and then it says that that two ends of the temperature, two ends of the rod are maintained at temperatures 0 and 100 degree, and the length of the rod is 2 meters, say 2. So that is your condition, and if you, this is a standard problem, you can solve it, even it is solved there in this book. So if you do this problem and you get the following, this below exact solution: txt equal to 50x plus summation over n equal to 1 to infinity 400 by n pi square sine n pi by 2. These are all prefactors, function of n, and e to the power minus n square pi square kt by 4. This is the time part, and then sine n pi x by 2. This is the space part. So this is your expression, and you do the same problem again with this boundary conditions. You write in this code, you just change it very little, and I have written in my own way. I have created to avoid the if logical if statement. In the program, I have created two arrays by linspace x1 and x2. One is between 0 to 1, another is above 1 to 2, and I then combine them by concatenation, and then I have created u with the keeping on the I with the given initial condition. This is your u 100 combination of this concatenation of 100 into x1 and 100 into np dot 1's 100. So you understand the how we implement the initial condition. You can write your own code, no problem. This is the way I wrote. Okay, so you put these conditions in your Python script, and oh, okay, u0 u200 also equal to 0 100. That are the two boundary conditions, and you get this result. See, the two lines overlap with each other. This is the result. Okay, so so we have seen now lots of various different kinds of problems with very many initial and boundary conditions, and you expect the result in a certain way, and you see by numerical your program, by computation, you get the desired results. Now you want to do some little more adventure. You want to see how the temperature profile goes. That means you want to see the dynamics, the animation of that. But we do here a very cheap animation without knowing any other further technical thing. This is very easy to do with a little trick. You wrote this x, u, these things as usual. Then you wrote the time and space loop as usual. Then you see inside this you want to know, suppose you want to see animation in a way that you want to check with time how the given initial delta function or narrow Gaussian or whatever, how that spreads with time. So you want to see a 3D plot like that. So now after the I loop, for I in range this loop, that means space loop, after this I loop is over, that means that is for one time step inside time loop. So now how do you create the animation? You can think that okay, you if you put one frame, show it, and then remove it and put another frame and so on, then it will look like a dynamic thing. It will look like a kind of animation is going on. Okay, here it will be not 3D, sorry, it will be 2D animation. So the profile how it goes with time. Okay, we'll show it you 3D. Okay, so to do that, you write plt.cl. plt is your matplotlib. Import matplotlib.pyplot as plt. Okay, so plt.cla is this function clears your area where your graph will be plotted. Otherwise, it will superpose with previous something, the frame. So it will clear the frame, then you plot, and then you pause for some time. Plt.pause, in bracket there is some seconds, 0.001 second. You can give any time, 1 second, 0.1 second, whatever. So these three lines, if you write these three lines inside the time loop, so it will clear first, then plot, then pause for a while, and then go for a time loop again and create the values for another time, and again it will clear and plot and pause. So if you do that, you can see a kind of animation that we will show now. So here we see it's like a time lapse video, and see how the temperature profile goes with time. So initial kind of delta function, and you see the spreading Gaussian, how it spreads with time. Okay, so the x-axis is the length of the rod, and y-axis is the temperature values. Okay, so now the next question you can ask, how the temperature of a point changes with time. That means maybe at the point you hit it, so the temperature you gave, initial temperature, say 1 or whatever, so how that goes with time. So lots of different questions you can ask within this simple scheme, within this simple problem. Okay, so to do that numerically, you have given x equal to np dot linspace 0 to 1 as usual, and you have given the initial and boundary conditions. U np dot 0 is 101 and u 50 equal to, that means you have equal to 1, that means you are hitting at the middle, as like the first problem we did. And to in the program to record this point, how the middle point, how this temperature goes, you can define that u0 equal to some empty list, then time t capital T equal to range 100, and then for time in capital T, and then the usual for loop for I, and you wrote this. And now you after the space loop is over, you can append the value. You can record this value u0 dot append, inside that u50, that means for the 50th this index point, you are recording this temperature value. So if you do that simple manipulation with this, you can, and you want to plot t versus t is your time range, time scale, and versus u0. u0 records all the I mean the temperature of the middle point for all the times. Okay, if you plot this, what do you expect? You should expect the temperature goes down with time. But how? You have solved this problem. Whether will this decay with time exponentially or not, that is up to you to decide, because we have solved the problem analytically. And now in numerically, what you should get, you get this temperature at heating point versus time. Okay, so the point is, you can do lots of these problems uh, um, with within this scheme of very simple program, and you just change the initial condition and boundary condition, or you want to see some parameter, something, some variable, how it changes with time or space or whatever. You can do that within this thing. Okay, but later for uh, more your purpose, you can write a more complicated program, including incorporating lots of different things. That is different. So this is the problem. So far we have discussed, the problem is a simple one dimensional insulated rod with two fixed boundaries at two ends and given initial temperatures at all the points on the rod. This is the problem. So we wrote this simple program. Okay. Well, I wrote the program in my own way in Python. You can write your own program, but always remember, is my suggestion is that you write a program in such a way that should be as minimal, as simple as possible. You know, Professor Dietrich Stauffer, he was a legendary statistical physicist, computational statistical physicist. He was in Cologne University in Germany. So he once told me that you should write a program, the length of the program should be less than your age. So that was fun. But he used to write in Fortran, and I used to write in Fortran also. Fortran was the most trusted computer language throughout 100 years among the scientists, even including NASA. So anyway, now we are in Python. We can write more beautiful program, more efficient program. Okay, but anyway, so this is the philosophy. That philosophy should remain with us. Next, for a 3D plot. So people who are more curious about uh, doing all kinds of fancy stuff, you can plot a 3D graph within this thing. But to plot a 3D graph, you know, in Matplotlib how you can do that. Okay, if you go to the chapter on Matplotlib in my book, you can see that it is shown there how the 3D plot can be done. You don't have to see all those details of the lines, but you only look at the lines written in the red color. So these lines are other lines are common. So here you see, notice J for first loop is J. I mean, this is a time loop. I just changed the name of the index. So for J in range 1 to 100, J is your time index. And next loop is for I in range 1 to 100. I is the space loop, and the rest are usual. And what I have written in between is that uj equal to uj minus 1. That means, but here also you see u is created in such a way. U is, I have not shown everything. U is now a 2D array instead of 1D array. Just we have to plot in 3D. So we have created U as 2D array. 2D array means one side is space and another side is time. So we have created a as if a mesh grid of with x and t. Okay, so you see in the line in this uji plus equal to uj I plus 1 minus 2 uji minus uji minus 1 by 4. So the same thing you would have written with two indices. Left side is the new time and the right side is old time. Okay, and in between the two loops you have written uj equal to uj minus 1. That means jth row now is I mean j minus ith row, the information is going to jth row. That means the each row is for one time. So the you have evaluated up to certain time, and this information is you are now taking as initial value for the next time, so that you don't have to start from the very beginning every time. So you evolve up to some time, and then you try to plot that, and then again you go from there, you start and you try to plot that, and that way you create a 3D plot. Okay, and now import matplotlib.pyplot as plt. Then from matplotlib you import cm is for mapping. Okay, and then the next line you write from mpl underscore toolkits import mplot 3D. That's for 3D plot. Okay, and then you have created capital X comma capital T equal to np dot mesh grid, and in bracket you write x comma t. That means you have created a mesh grid with x and t arrays. X and t arrays you have defined at the beginning. Well, then you have written figure equal to plot dot figure. This you can write, you may not write. And then axis x equal to plot plt dot axis, and inside that you have written projection equal to quote unquote 3D. That will give you 3D plot. Okay, okay. Next, ax dot plot underscore surface. You have written plot underscore surface. Inside that you write capital X capital T, because this has created 2D mesh grid, and then you write u. U is the third axis, means z axis. So the mountains will be with u. So this u, and then you write cmap equal to that you have imported cm dot coulomb. This is a special coloring scheme, texture scheme. So that is for your design, and then you write plot show. So next in this next video we will show how we can do this. So you see the temperature profile. The left side is the initial Gaussian, and the right side is the Gaussian after certain time, and you see the height is reduced and the Gaussian is spreading, right? Okay, now we come to the last part of this talk. We extend the calculation, the computation in 2D. So we did the problem with 1D diffusion, and we just add a little and we get the diffusion in 2D. So for that we have to write this diffusion equation. Just you add one extra term, del to u del y square. Okay, so and the left side is del u del t as it is. So if you discretize this again in the same way, left side you discretize with forward difference formula, and now your superfix k is your time index. So left side is uij k plus 1 minus uij k by delta t, and the right side two space derivatives you do with central difference formula as we did earlier. So now we have the two differences, delta x and delta y. You can take delta x equal to delta y, and now you have I is x index and j is y index. And since you take delta x equal to delta y, once again you will have the on the right side delta x square by delta t by delta x square and delta t by delta y square, and you take that as r again. So with this, like the previous, so you have the discretized explicit equation for evolving u at certain point ij for a time given on the right side, that all the values ui plus 1j, ui minus 1j, uij, uij plus 1, uij minus 1, all the terms, all are evaluated at the older time. So the left side is the new time and the right side all are, you see, look at the index, all are k. Okay, so it is again can be done easily, like the same way you can solve the problem so easily. So you implement this program, and you see, before you implement the program, you can visualize in a little better way on the to imagine what we are going to do. Take a square lattice. That means it is a system, say, on the x-axis, on the yeah, this is the x-axis on the horizontal and the y-axis on the vertical, and you take any point, say ij. So you have to know to I mean, the time is not shown here. Okay, so to evolve the value of u at any point ij, so what you have to do, you need the information of its four nearest neighbors: I plus 1j, I minus 1j, right side, left side, above I j plus 1, and the below I j minus 1. So you need now four values at each time. So no matter, you can do that. Okay, so what we do is we try to write the program in the same way. I'm not showing everything, but the essential part. So you have to now create x and y, two numpy arrays, and you have to create u as a 2D array, np dot zeros 101 comma 101. So you have created a 101 by 101 square mesh, and you give the initial condition u 50-50 equal to 1, as if you are at the middle of the square net or the system. You have given the value 1, so 1 delta function, or you could give a Gaussian also, xy Gaussian. And there is a time loop, time in range, say 200, and then there is a space loop, I is for x, and then there will be another loop for j in range 1 to 100, say, because the x extends from 0 to 100 uh, indices, and the y also ranges from 0 to 100, and the 0th point and the 100th point you are not updating on all sides. Okay, so x direction, y direction, on all sides, on the boundaries, four boundaries, you are not updating the boundary points. So you are updating the inside points, but of course you need the information of the four boundaries, and you write these expression uij. Now we have two indices uij. Time index is not index is not again given here. I don't need this. So uij plus equal to u I plus 1j plus uij plus 1 plus u I minus 1j plus ui j minus 1 minus 4 uij 4. Okay, so this was the problem. So okay, anyway, before I conclude, I'll show you the video. Okay, so you see the 3D plot, how the Gaussian spreads over the network in time. Of course, for that you have to do write a program to do 3D plot. Okay. Okay. So this is the last slide. So here the two problems are given. You can do them easily. The first one is easy. With a given distribution sin pi x by L distribution, you obtain the following expression: tx equal to sin pi x by L into the exponential time part. So by little manipulation of your program, you can do this easily now. And the next problem is where you have included the Newton's law of cooling. So far you are doing the problem where you had insulated the rod. Now you allow Newton's the cooling radiation. So you add an extra term, say on the C, the last formula, minus lambda into T proportional to, so the lambda is some constant, you keep some constant and you solve the same problem. The k by 0 is actually the d square. You can choose your own unit and you can now write little bit, you manipulate the code, rewrite the code in a little the add the term, and you see, check how the effect of radiation changes the time profile. So that's it.